So, how do you solve differential equations? Well, it depends. There are different techniques that you can use on different differential equations. Some techniques work on some equations, but they don't work on others. In this video, I'm going to talk about something called separation of variables, which might be the simplest approach in the sense that if your algebra and calculus skills are really solid, you don't need to learn much extra to solve differential equations this way if they can be solved this way. So let's look at how this works. First of all, remember from calculus that the expression dy dx, a dy on top over a dx on the bottom, stands for the derivative of y with respect to x. And it looks like a fraction or a quotient, one thing divided by another thing. It's not really a fraction, it's really a limit of a fractional expression, but in many situations you can treat it as if it were a fraction. In particular, in calculus, dy by itself is typically defined to be dy dx times dx. So for example, if y stood for the function x squared, then dy dx would be the derivative with respect to x, that is 2x. So dy by itself would be 2x times dx. You've seen this if you've learned about integration and integration by substitution or integration by parts or things like that. Now, let's say we have a differential equation, a first order equation set up in the form dy dx equals whatever. So you got dy dx on one side equal to whatever it's equal to. And suppose I multiply both sides of this equation by dx. Then on the left, we have dy dx times dx, which is just dy, and that's equal to something times dx. So you got dy on one side and dx on the other side. So a first order differential equation could be written in the form dy dx equals something, or it could be written in the form something times dy on one side equals something times dx on the other side. Or you could get it all on one side of the equation and write it as something times dx plus something times dy equals 0. And those somethings could involve x or y or both. Now suppose you've got the equation set up with something times dy on one side equal to something times dx on the other side. Now, like I said, those somethings might involve just x, they might involve just y, or they might involve both of them all mixed up together. But if you're lucky, you can get it so that the thing in front of the dy, the coefficient function for dy, only involves the variable y, and the coefficient function that's being multiplied by dx only involves the variable x. And if you can do that, then the equation is said to be separable. And the process of putting the equation into that form so that you can deal with it is called separation of variables. And the nice thing about this is that if you've got it set up this way, with all the y stuff on one side and all the x stuff on the other, you can integrate both sides. You can say that the integral of a of y dy equals the integral of b of x dx. So you can go from the equation involving the derivative or the differential into an equation that relates x and y themselves, which gives you the solution to the equation. So let's look at an example or two. But before we do that, in the next example I'm going to show you, I'm going to be taking advantage of some of the properties of logarithms and exponents, which you can see here. So if you need to pause the video and take a second to look these over, you can. But I don't want you to think I'm pulling something over on you when I use these in a few minutes here. So let's take the differential equation dy dx equals 3y over x. So this means we're looking for a function so that the derivative of that function is equal to 3 times the function divided by x, the variable that the function depends on. And I'm going to start by multiplying both sides by dx. So on one side, dy is equal to, on the other side, 3y over x dx. Now I want it so that in front of the dy, we have a function that only depends on y, and in front of the dx, we have a function that only depends on x. Now right now, in front of the dx, we got something that involves x and y, and we don't want the y there. So to get rid of the y, since it's something times y, I could just divide by y on both sides of the equation, or equivalently multiply by 1 over y. So if I do that, then I get 1 over y times dy equals 3 over x times dx. And there I have separated the variables. I've gotten it into the form where we have something just involving y times dy equals a function only of x times dx. So now I can integrate both sides. The integral of 1 over y dy equals, and 3 over x really means 3 times 1 over x. So I've taken the liberty of pulling that constant multiplier 3 outside the integral. So it's 3 times the integral of 1 over x dx. Now to actually do the integration, you just have to remember that the integral of 1 over y dy is the natural log of the absolute value of y plus a constant. Then on the other side, 3 times the integral of 1 over x dx would be 3 times the ln of the absolute value of x plus a constant. And you might be tempted to just write plus c on both sides and then have the c's cancel. But that wouldn't be right because it's not necessarily the same constant on each side. An antiderivative of 1 over y would be the natural log of the absolute value of y plus some constant, and that constant could be any number. And on the other side, we get plus some constant, which could be any number, and it's not necessarily the same number as it is on the other side. So I labeled one of these C1 and one of them C2 to keep track of the fact that they're not necessarily the same number. But what I can do is I can subtract C1 on both sides of the equation. And now it's natural log of the absolute value of y equals 3 times the natural log of the absolute value of x plus C2 minus C1. And if C1 and C2 individually could be any number, then C2 minus C1 is just any number. It's just some arbitrary constant. So I could just go ahead and call that C and write natural log of the absolute value of y equals 3 times the natural log of the absolute value of x plus c. So this shows that you really only need a plus c on one side of the equation. So when you integrate both sides, feel free to just put a plus c on one side. That's what I'm going to do in the next example I'll be doing. Now, in one sense, we're kind of done solving the differential equation. We've got sort of a solution. We've got an equation here that tells how y and x are related, so it implicitly gives us the solution, what y has to be as a function of x, but it might be nice if we could solve it explicitly for y. So let's take this equation and try to get y all by itself on one side so it tells us what y is equal to in terms of x. So to undo the ln, we need its natural enemy, or its inverse, the exponential function. So we're going to exponentiate both sides. We're going to say e to the left side of the equation equals e to the right side of the equation. Now remember, when you have e to the something plus something, that breaks up into e to the first thing times e to the second thing. So I've rewritten e to the 3 times ln of the absolute value of x plus c as e to the 3 times the natural log of the absolute value of x times e to the c. Now, e to the ln of anything is just that anything. They undo one another. And e to the 3 times the natural log of something is equal to just the something to the 3 power. So in place of e to the 3 times the natural log of the absolute value of x, I just have the absolute value of x to the 3 power. The absolute values on both sides mean that the two sides could just be equal to one another, or they could be opposites. One could be positive and one could be negative. And we can show that by writing y itself equals plus or minus x to the third times e to the c. Now, if c is any constant, e to the c is some positive constant. But with the plus or minus in front of it, we get that the plus or minus e to the c could be any positive or negative number. So I'm just going to write it as c, which could be positive or negative. So this c here is a different c than here. This c stands for plus or minus e to the c, but it turns out just to be an arbitrary constant. So there's our solution, and we can check it by, well, if y is c times x cubed, then dy dx, the derivative of y with respect to x, would be 3cx squared. So that takes care of the left side of the equation. Meanwhile, over on the right side, 3y over x would be 3 times cx cubed over x. And if we simplify that down, divide out an x, that simplifies to 3cx squared. So the left side and the right side are both equal to 3cx squared, which means they're equal to each other, and the differential equation is true. Let's look at one more example of a separable differential equation. dy dx equals 1 plus y squared times x. To separate the variables, I can multiply both sides by dx. Now, I don't want any factor that involves y in front of the dx. So I'll divide both sides by the factor 1 plus y squared. Now I've separated the variables, and I can integrate both sides. The integral of 1 over 1 plus y squared dy equals the integral of x dx. Now you remember the integral, or the antiderivative of 1 over 1 plus y squared with respect to y is the arctangent of y. And the antiderivative of x to the first power is 1/2 x to the second power, plus c. Remember I said you only had to put the plus c on one side of the equation. Now, to solve this for y, to get what y itself has to equal, I can just undo the arctangent by taking tangent of both sides. Tangent of arctangent of y would just be y, and so that's equal to the tangent of the quantity 1/2 x squared plus c. Now, there's our solution. Let's visualize this. Here's our differential equation, and here is its slope field. Remember how this works. At every point in the plane, we got this little slope marker. It's a little line segment with the slope of that line being determined by 1 plus y squared times x for the x and y coordinate at that point. And by looking at those slope markers, you can get an idea of where the solution curves would have to be going and what direction they'd be going in. Now, the solution we got was y equals tangent of 1/2 x squared plus c, where c is any particular number, any constant. Could be 0, could be 1, could be 2, could be negative 13. If c is 0, then we're just looking at y equals the tangent of 1/2 x squared. And the graph of that is shown here. It's the blue graph. If c is 1, we get y equals the tangent of 1/2 x squared plus 1. That's what's graphed here in green. And if c is 2, we get y equals the tangent of 1/2 x squared plus 2. And that's shown here, that's the red graph. We get other graphs for other values of c, and together they give us the whole family of solution curves to this differential equation. Now, of course, what we've been doing here, separation of variables, doesn't always work, because lots of differential equations, you can't set it up so that you just have something involving x in front of the dx, and then just something involving y in front of the dy. For those situations, you might have to use some other technique. But when you can do this, it's usually the easiest way of solving a particular separable differential equation.